This video also is going to deal with linear transformations, but we're going to stick with a linear transformation that operates on vectors in R2 and returns a vector in R2. So these transformations will be easy to kind of picture as points in a two-dimensional plane being moved around. Specifically, the linear transformation that we're going to look at in this video is the transformation T that takes a vector from R2 and returns R2. And what it does is it rotates points about the origin in a clockwise manner, and it rotates them by pi over 6 radians. After rotating by pi over 6 radians clockwise, it then reflects that point through the line described by the equation x1 equals a negative x2. So it's a single linear transformation, but that single linear transformation can be decomposed into two steps, a rotation followed by a reflection. What we're going to do is we're going to find the matrix representation of this linear transformation, and then when we're done doing that, we're actually going to compute what is the linear transformation of the point 1, 0. What happens to this point 1, 0? That's a point on the x1 axis as it gets rotated and reflected. So we'll get to visualize what this linear transformation does at the end. So the first component of this linear transformation is a rotation. So a rotation in a clockwise direction about the origin can be described by this matrix: cosine theta, sine theta, minus sine theta, cosine theta, where theta is the amount of the rotation performed in terms of radians. This is a clockwise rotation. If it was counterclockwise, we would have negative sign here and positive sign here. So it's easy to switch this rotation matrix from a clockwise to a counterclockwise as needed. For our specific case, we're not rotating by theta radians, we're rotating by theta equals pi over 6. So if we replace all the thetas with pi over 6 and compute cosine theta and sine theta, our rotation matrix turns into this matrix right here. So if we were just doing a single rotation, we'd be done. This would be our matrix representation, but this is just one part of the full linear transformation in this problem. The other part that's happening that we haven't talked about yet is the reflection. We're going to reflect about the line x2 equals a negative x1, or you can think of it as x1 equals a negative x2. Same equation. That operation is described by this reflection matrix here: 0, negative 1, 1, negative 1, 0, I'm sorry. Let's check. Let's think about why this works. Anytime you want to know how a linear transformation is operating on something, you can just pick an arbitrary element, x. In this case, x has just two components, x1 and x2, and we can just operate on this arbitrary vector to see what happens. So if we start with the vector x1, x2, and then linearly transform it by this reflection operation, we end up with x1 times the first column plus x2 times the second column, which turns into a negative x2 and a negative x1. So you can see what happened. Originally in our vector we had x1 here. x1 has changed to the second coordinate and been negated. Same thing with x2. Originally we had x2 here in the second coordinate. Now x2 is in the first coordinate and it's been negated. Well, that's exactly what our equation says should happen. x1 should turn into a negative x2. x2 should turn into a negative x1. So this matrix is doing exactly what we wanted to do in terms of reflecting it about the line that we're supposed to reflect it about. So that makes sense. So let's put these together now. Our final matrix representation of this linear transformation is just the product of these two individual operations. The first thing that happens is we rotate, so we have to write that on the far right, and then the next thing that happens is the reflection. So the order of this is very important. Since we're going to be multiplying by a vector here, the first thing right here needs to be the first operation, a rot followed by a ref. So you can kind of think of this stack as the last operation, the next to last operation, all the way down the line in that order. So let's go ahead and compute what this is. So this is just these two matrices multiplied together, and if we do that, we end up with this final matrix for A. So this is the matrix representation of the linear transformation that we were trying to find. Let's go ahead and do the second part of the problem, though. Let's think about what happens when this linear transformation operates on the point 1, 0. Well, we know what that means. That means take the vector 1, 0 and multiply it on the left by the matrix A. So that's this quantity right here. If we actually do that multiplication, when we multiply A by 1, 0, that really selects the first column of A, so we end up with the first column of A. Let's try to picture what's going on there. Here is the R2 plane. Here is the unit circle in purple, And we're starting off at the point 1, 0, right? We start off with 1, 0. So right here, we go 1 unit along the x1 axis and 0 units up the x2 axis to start right there at 1, 0. The first thing that happens in our linear transformation is we get multiplied by a root, right? That's the first thing that happens. We get multiplied by a root, and then we get multiplied by a ref. If I take a root times 1, 0, I end up with the point square root 3 over 2, negative 1/2. Well, that's this point right here, square root 3 over 2 minus 1/2. I've been rotated pi over 6 radians in the clockwise direction. Okay? What happens next? The next thing that happens is we're going to get reflected about the line x1 equals a negative x2. So there's my best stab at drawing a straight line through the origin with a negative 1 slope. And we're going to get reflected about that line. So if we do that multiplication, if we actually take this vector times a ref, we actually get the point 1/2 a negative square root 3 over 2. That reflects us about the line x1 equals a negative x2. So this point right here, I'm sorry, I meant to circle it, not draw a line through it. This point right here we computed by just taking a ref times this point right here. So starting at this point, what happens next is the reflection operation operates on it to reflect it down there, and that operation is described by this multiplication, which gives us this vector right here. So you can see I've been reflected about the line x1 equals a negative x2. I've hopped from this point, and I've been reflected over to this point. So that's the end of our example. We've computed the matrix representation of a linear transformation that rotates then reflects a point. And we were able to break that down into these two pieces, a reflection operation and a rotation operation. The biggest thing to be careful about when you work these problems is that in general, a ref, a rot is not equal to a rot, a ref, right? Matrix multiplication, the order matters almost always. So just make sure that when you write down an operation like this that consists of a sequence of steps, you have those steps written down in the right order.